of my summary. It's a very concise summary. I'm not claiming to go into every detail. We'll get some of the details later on. But basically, this is the Standard Cosmological Model. The entire universe is contained initially in a point that they call a singularity. There are different types of singularities in physics. This is one type in which all the energy and matter and space itself are collected into what we might think of as a zero-dimensional entity, a point, something that has no size, a singularity. And then, there's a misconception here because some people think, well, this is a point in space, so it's surrounded by empty space. All the mass of the universe is collected into a point surrounded by empty space. But actually, it's not even surrounded by empty space because even space is in the singularity, okay? And that seems a little bit weird, but it's not my model. So anyway, by the way, there are other types of singularities that are surrounded by space, and I think some of those might actually be real. But in any case, this point then rapidly expands like a balloon, so it goes into a three-dimensional space which expands. Now, there's a lot of misconception on this because this is an analogy, and the surface of the balloon, which is two-dimensional, because it has height and length, but not really any substantial depth to it, right? I mean, a little bit, but not much. That two-dimensional surface is supposed to represent the three dimensions of our universe, the three dimensions of space, okay? And so, just as an ant on a balloon could walk all the way around it and come back to the starting point, in some models, in some versions of the standard model, in three-dimensional space, you can go straight out and yet eventually come back to where you started because it's wrapped around it. You can think of it as being wrapped around a fourth spatial dimension. Most physicists don't think of it that way, but if that helps you to conceptualize it, that's fine. You can embed it in an artificial dimension that way. So as it expands, then all the energy that is contained in everything that will become everything, that expands as well. And it cools. Because, that just follows from the ideal gas law, because you have the pressure dropping tremendously and the volumes increase, the temperature is going to drop as well as it expands. Initially, at this point, there's no actual matter in the universe. We don't have things like atoms of hydrogen or things like that. Certainly not the heavier atoms. It's electromagnetic radiation, a lot of that, and you'll have subatomic particles that pop into existence and pop out of existence from the substructure of space. Now, as it expands, it cools, and that energy cools to the point where it can become matter. And so some of that energy, some of it, is transformed into the two lightest elements, hydrogen and helium, which are both gases, and just a little bit of lithium, the third lightest element. And there are various stable isotopes, but unstable ones too, but then they decay. It doesn't make any of the heavier elements. Only the lightest three. Elements number 1, 2, and 3 on the periodic table are supposed to have been formed by the energy from that initial Big Bang, from that initial, as the energy cools. And we'll take a look at that a little bit later on in some of the issues there. But of course, at some point, you got to make the heavier elements. So that's going to be an issue. How do you do that? Well, you're going to do it with stars. Because the next step is some of that hydrogen and helium collapses it into stars. By the way, some of the energy remains energy, and it continues to stream out into space, and they think that's what makes the cosmic microwave background, which we'll talk about later. Some of it forms hydrogen and helium gas. Some of that just remains gas, and you'll see we find these enormous nebulae out in space, large clouds of hydrogen and helium gas. But some of those clouds supposedly have condensed into stars. Under the force of gravity, it's supposed to pull them together into stars, and the stars collect into galaxies. And there's been some debate over the decades as to whether the galaxies form into stars, or whether the stars form first and then collect into galaxies. And in any case, there are slightly different versions of the standard model, but I'm just giving you sort of the nuts and bolts, the basics of it. Now, those stars then create heavier elements. The idea is that in the core of stars, you've got fusion going on. And actually, I think there's good evidence that stars like the sun fuse hydrogen into helium, like a big nuclear bomb, so to speak, although the actual rate isn't as much as people think. But because the temperature in the core of the sun is so great and the pressure is so great, you can actually ram protons together, and through a process, the proton-proton chain, you get helium from that. So helium is the byproduct. Of course, you've already got helium in the universe, so that doesn't help you very much. But the idea is that some stars, when they then run out of hydrogen in their core, they'll begin fusing helium, which requires a different, pressure, higher pressure and temperature, but the star is supposed to collapse in a little bit, and then it initiates the helium flash, and then it starts fusing helium, and then it starts fusing the next element. When it runs out of helium, it fuses the next element, and the next element, and the next element, and so on. So you can get heavier and heavier elements up to iron. And you can't do anything heavier than iron, because reactions after iron are endothermic. They don't release energy, they absorb energy. And so you can't power a star that way. Okay, you can't, release energy by losing a little bit in every step. That's not going to work. But the idea is that some stars are so massive that at the very end of their life, when they've fused all the fusible material up to iron, there's this implosion that, even though the reaction is endothermic, it produces chains of these higher elements all the way up to uranium, for example. And so it's only in a supernova, an exploding star, that secondary astronomers believe you can form the elements heavier than iron. And so that is supposed to account for all the rest of the elements on the periodic table, which is a lot of them, right? But it's kind of interesting to me that the actual Big Bang, the initial expansion there, only forms 3 elements. And there are around 90 naturally occurring elements in the universe. The Big Bang accounts for 3 of them. And then they have to explain the other almost 90 by stellar nucleosynthesis, and in particular, just the supernova reaction to get the really heavy stuff. And the idea is that some of that then gets blasted out in space as dust. Dust is made up of heavier stuff heavier than hydrogen and helium. And then the idea is that some of that dust, some of it remains in space, some of it condenses and forms planets like the Earth, and so on. You can even form the core of the gas giants, and then they can collect hydrogen in their envelopes there. And so this is the model that explains the universe as it is today, because we do have heavier elements today, right? We have elements all the way up to uranium, and well, okay, they're made in supernova. Okay, well we have hydrogen and gas. How do you get that? Well, it's made from that initial energy. Okay, the universe seems to be expanding. Well, yeah, that's because it started that way. And we have planets. Well, they formed from the dust. And so it does account for the universe that we have today. But my question is, which of these steps are scientific in the sense that they are observable and repeatable in the present? Let's think about that, because we're told that this is the scientific version of origins, right? And you crazy creationists, you believe in all this silly magic and everything. This is the science version, right? Well, science, in an operational sense, is always about testability and repeatability. You learn that in high school. You learn about, you have to do an experiment that can falsify your hypothesis and so on. Which of these have been repeated in a laboratory or have been observed in the actual universe? Have we in a laboratory contracted a universe into a point? Well, no. We've never seen a universe that is zero-dimensional, and I'm not sure how we would anyway. But that would seem to be a bit problematic. It's certainly not something that we've observed. We have not observed that a universe can be a point. It's not science. A point rapidly expanding like a balloon. Well, I do think there's evidence that the universe is being stretched out, or at least has been stretched out. I think that's even biblical. But in terms of being stretched from a point, we have not seen that. No one has seen space-time being stretched from a zero-dimensional structure to a three-dimensional structure, 3 dimensions of space, one at a time, right? We've not seen that. It's not observed. You can't repeat that in a laboratory. How about energy becoming matter? Can we take energy and make matter from it? And the answer is actually yes, we can. This is something that we can do in particle accelerators. We can take particles and slam them together at very high speeds, and some of their kinetic energy will manifest as new particles. Pretty neat. So you'd say, well, there you go. That step's confirmed. Not really, because the claim is not that energy can be converted into matter. If that were the claim, it would be verified. We can do that. The claim is that all the matter in the universe was produced that way. That's a different claim, isn't it? It's one thing for me to say, your freezer can turn water into ice, which it can. You can verify that scientifically. It's quite another thing for me to say, all the ice on the earth was produced in your freezer. See the difference? Energy can become matter. Have we demonstrated that all the matter in the universe was once energy? We haven't demonstrated that. So I'm going to call that plausible, but it's certainly not, it hasn't been verified scientifically. We just know that it's possible scientifically. with a caveat. We'll see there's some problems with this as we go later on. Have we seen matter being condensed into stars and galaxies? No. I know you've read, oh, but this is a star-forming region, right? Let me clue you in. No one has seen a star form. No one has seen that observationally in terms of gas that's actually collapsing in on itself. It's measurably collapsing in on itself into a tighter space. We've not seen that. Gas in space is either stable as a star or it's expanding in a nebula. It's not contracting in on itself. We've never seen that. And so it's certainly not something that has been scientifically observed. Now, I'm not saying at this point that it's impossible, but I am saying it has never been observed or demonstrated scientifically. What about, have we observed that stars can make heavier elements? Well, I think there's indirect evidence that you can get hydrogen into helium. I think there's pretty compelling evidence for that. But in terms of making elements heavier than iron in a supernova, that's very questionable. It's certainly not something we've observed. Nobody has observed a supernova that we know enriches the interstellar medium after the explosion. We haven't measured the interstellar medium before and after and find that it's enriched with heavier elements after the explosion. We've not observed that. We've not observed that. In fact, there are some physics problems making some of these heavier elements because of the way they're supposed to form. It's challenging in terms of the science there. Have we seen dust condensed to form planets? The answer is no, we've not seen that. In fact, we haven't even been able to really simulate it properly. The simulations show that you can get dust to accumulate into little sort of dust bunnies, but then that's all the bigger they get, because after that, collisions tend to fragment them apart anyway. So not only has that not been observed, we can't even really simulate it. So think about that. I mean, of the 6 steps in the scientific version of the origin of the universe, 5 of them have not been observed scientifically at all, and one of them is plausible, but it hasn't really been observed. So I think it's interesting that really no step of the Standard Cosmological is operational, observational science. It just isn't. And some people would say that creation hasn't been scientifically observed either, and I'd say that's true, but creation doesn't claim to be a scientific fact. Creation is an historical fact, one that makes science possible. And so it's in a different category, and we do have good historical evidence for creation, and it happens to line up with the science that we observe today. So, a model in science is a schematic description of a system theory or phenomenon that accounts for its known or inferred properties and may be used for further study of its characteristics. That's the dictionary definition of a model in a scientific sense of the word. Now, the Big Bang does count as a model because it is a schematic description of a system or theory, in this case, the universe, that accounts for its known or inferred properties. It accounts for why the universe has stars, why the universe is made of the atoms that it's made of, primarily hydrogen and helium, and trace amounts of the other stuff. It accounts for why there are planets. I don't think it accounts for them correctly, but it does account for them. And so it counts as a model. It does explain these things. The explanation is wrong, but it's an explanation. And it may be used for further study of the characteristics, indicating that it will make predictions about what you would expect to find in the future. So anything counts as a model. We have various creation models as well. We discussed some of those during the panel discussion. But what makes a good model? A good model is, first of all, relatively simple. And sometimes laymen mess that up. They think something's got a lot of equations and it looks very complicated, it must be true. But really, it's the reverse. You've heard of Occam's razor. And when you have competing models, the one that has the fewer assumptions tends to be more likely to be it's certainly better, and it tends to be more likely to be true. And nature seems to prefer simplicity. It's because nature is upheld by the mind of God. And there is a simplicity in Christ, the Bible tells us. So the fewer assumptions, the better, assuming the two models make the same predictions, right? And then, of course, the second characteristic is a good model has to make many correct specific predictions. It needs to make many correct specific predictions. It's not good enough to make one, right? Even a blind squirrel gets an acorn every now and then. That's not impressive. An incorrect model will occasionally make a correct prediction. It needs to make many correct predictions. They need to be correct, of course. If the predictions are wrong, your model's falsified. Yeah, if people really approach it that way, they'll tend to modify their model. Well, you can do that, but then it's a different model, isn't it? And the predictions need to be specific. The more specific, the better. If I had a model and I said, my model predicts that tomorrow something will happen, And then lo and behold, tomorrow something happens, and I say, there you go, my model's verified. That's not very specific, is it? Because any model predicts that, or just about any. So it needs to be a specific prediction. Examples of good models would be the heliocentric model for the solar system, the idea that the planets orbit the sun, and Newton's laws of gravity and motion. These are examples of good models in science. The heliocentric solar system is not the only one that's been proposed. There was the geocentric model, which had the planets all orbiting the Earth, and the Ptolemaic system had that. But to get that to work right, in order for it to be consistent with observations, you had to make the planets make little circles as they go around the big circle, right? The little circles, the epicycles that go around the different, and that's kind of complicated. But the interesting thing about this is it works. Did you know that? You can make correct predictions using this model. The Ptolemaic model was used for over a millennium because it tended to make pretty good predictions. Copernicus came along and said, let's put the sun at the center. He wasn't the first to come up with that idea, but he revived that idea. And the main advantage of the Copernican model is not that it makes better predictions. His predictions were about the same as Ptolemy's. Because even he didn't have it quite right. He assumed perfect circles. They're not. They're ellipses. But in any case, the main advantage of the Copernican model is it's simpler. You don't need those epicycles. You can account for retrograde motion naturally as one planet passes another in its orbit. And so that's an example of a good model. Newton's laws of motion and gravity. Those are fantastic because think of how simple those are. You got Newton's 3 laws of motion and his law of gravity. You can write those on an index card. And from those 4 principles, you can predict the motion of just about anything in the universe, at least in non-relativistic limits. That's amazing. You can actually explain why planets orbit the way that they do and so on. In fact, Newton's laws were so successful that they predicted the existence of the planet Neptune. The planet Uranus was off in its orbit from where it would be if there were no other objects out there. And 2 mathematicians independently realized that there must be another planet pulling on it, and they calculated its position. And one of them sent the coordinates into the observatory, and that very night they pointed the telescope. He said, if you point your telescope here, you will see a new planet. And lo and behold, they pointed the telescope there and found Neptune. That's awesome. See, that is a bold prediction. It's a very specific prediction, right? You point your telescope here, you'll see a new planet. And that's bold because most places you point a telescope, you will not see a new planet. Right? I mean, you had the rest of the universe, and Neptune wasn't there. It was right in the spot where they predicted. So that's an example of a good model. It makes many correct specific predictions, and of course today we can use Newtonian mechanics to predict the positions of the planets into the distant future. It works very, very well. So how does the Big Bang, the Standard Cosmological Model, how does it stack up? Is it relatively simple? Well, I've simplified it into 6 steps, but really the latest versions are very, very complex, and they have a lot of arbitrary assumptions built into them. There's inflation, there's quintessence, all these different parameters that they've had to add, I think, as band-aids to get the model to line up with observations. So it's really not very simple. Now, I would argue it started out pretty simple. The first version of the Big Bang that Lemaitre produced back in 31, it was relatively simple, but the latest versions are not. They're quite complex, and a lot of arbitrary knobs that you can turn to get things to work out right. Does it make many correct specific predictions? And the answer is no. Now, I'll give them one, and that's the cosmic microwave background. The Big Bang predicted that there should be microwaves coming from all directions in space. If you could go outside at night, if you could see microwaves, you'd go outside on a clear night and you would see the sky would be aglow with microwaves coming from all directions in space. And that's something that the Big Bang supporters, in fact, predicted, and they were right about that. It sounds impressive until you give it a little bit of thought, and then you think, well, it's not really as good of a prediction as you might have guessed, because they predicted that this would have a characteristic temperature of about 3 degrees above absolute zero, which is within, it's 2.7, that's in the right range. But there was other predictions that were as low as 1 and some as high as 50, and so there was a range of different predictions, and they happened to pick the one that happened to be right. It also predicted that there should be variations in these microwaves, hot spots and cold spots that are at least 10 times more intense than we actually find. So in other words, the cosmic microwave background is much more uniform than was predicted in the Big Bang model. They've come up with ways to try and account for that. But my point is, it doesn't make many correct specific predictions. It's made one, and it wasn't all that specific, and it wasn't all that correct. So the Standard Cosmological Model is not good science, just on the face of it. It's not compatible with the Bible. I don't want to spend a whole lot of time on this because I suspect you know a lot of this, but just because you might need to share this with others. A lot of people think, well, couldn't God have used the Big Bang to create? And the answer is not unless he's a liar, because that's not what he says he did in Genesis. You need to understand that the Standard Cosmological Model is naturalistic. It attempts to explain the cause of the universe without God. I have a number of textbooks that describe the Standard Cosmological Model. None of them say God started it. And so this idea that, Hugh Ross says, well, you see, that shows that God started the universe. I'm afraid that most astrophysicists don't see it that way. They would say it was caused by a quantum fluctuation, or it was caused by nothing, or maybe we can't know. It's not caused by God. It's not a supernatural act of God. But the Bible indicates God spoke the universe into existence. The time scale, we can't sweep that under the rug. The Standard Cosmological Model requires billions of years to get the universe from its initial point to the way it is today. Whereas the Bible indicates that the universe is only thousands of years old. It only took 6 days for God to create and get it to the point where it was absolutely perfect. And even there, it's not like he needed that time. He just did it that way as a pattern for us. So that's where we get our 7-day week. The order of events is different. A lot of people think if you can make the days of creation long periods of time, then you can let the Standard Model line up with the Bible. No, you can't, because the Standard Model has stars forming long before the Earth. And they have to, because remember, the heavy stuff that the Earth's made of is supposed to be produced inside supernovae. So you have to have not only stars, you have to have at least a generation of stars to make some of those heavy elements. And of course, if you follow the Standard Cosmological Model all the way into models of secular models of Earth formation and such, you find that the secular view is that fish evolved before trees, but the Bible has trees on day 3, fish on day 5. The secular view has dinosaurs evolving before birds, but according to the Bible, birds are created on day 5, dinosaurs are made on day 6. And so the order of events is quite different. The future, the Standard Cosmological Model is not just a story about the past, it's a story about the future, the way the universe will be in the future. Is supposed to continue to expand, and eventually, due to the second law of thermodynamics, everything runs out of usable energy. It gives up all of its heat, and we call that a heat death, because there's no longer any exchange of thermal energy. Everything's sort of run out of heat. And that's very different from the future that the Bible indicates. The Bible indicates a heat destruction, if you will, and a new heavens and a new earth that will remain perfect forever. They'll be very good, just like the original earth was before sin. So the future is very different. In the Standard Model, you'd expect life evolves wherever chemistry's right. It's a big universe, chemistry's probably right out there somewhere, so ETs are likely to be found, whereas, and I'll grant the Bible doesn't say there's not extraterrestrial life out there, but nonetheless, the Bible does indicate that God formed the earth to be inhabited. It's designed for life, and he doesn't say that about the other objects that he created for his glory and to be for signs, seasons, days, and years. The original Earth, according to the Standard Cosmological Model, is molten rock. It's supposed to have collapsed from that nebula and be very warm when it first started. According to the Bible, it was created as a paradise. It was created from water, right? God initially made it as water, and then brought the land forth and so on. And by the 6th day, it was a paradise. So it's very, very different. So it's not compatible with the Bible. There's scientific evidence that challenges the Standard Cosmological Model. That's probably why you came. You want to hear that. So without further ado, here's some of the problems. And I'm just going to focus on the problems that are in the secular literature. Now, Big Bang supporters might say, well, we've got an answer for that now. Okay, we can deal with that. But these historically have been problems with the Big Bang, and I think they really still are, to be honest. I think we can solve. You have the flatness problem, the idea that the expansion rate of the universe is very finely balanced with gravity. So expansion tends to make the universe bigger, gravity tends to want to stop that and make it smaller, and those two things are very, very well balanced, like a pencil standing on its end, on the sharp end. And it turns out when you run the equations backwards, in order to get that flatness today, they would have to be even more flat at the very beginning. They would have to be more finely balanced, which I suppose isn't a problem if you believe in God, if you believe in that God created the universe. You'd expect them to be somewhat balanced even today. But if it's just physics that somehow gave rise to these things, you wouldn't expect that, because any range is allowable. We have the horizon problem. Now, this is interesting because this is a light travel time problem. And the Big Bang supporters like to chide creationists for having a light travel time problem. I think ours is far more resolvable than theirs, because it's not a starlight issue per se, but the idea is that in the Big Bang, when it first starts, when the universe is very small, it's going to have different temperatures in different places, hot spots and cold spots, okay? And then the universe balloons out very rapidly, so now those spots are very far away from each other. And yet today, the temperatures are almost the same everywhere. The cosmic microwave background is very uniform. It does have minor increases and decreases, but the hot spots and cold spots, the real intense ones, are gone, which means the energy from the hot spot must have somehow got to the cold spot, right? It has to exchange energy. You put your ice cube in your hot coffee, you end up with warm coffee eventually, but they have to exchange energy. And the problem is, even if you give them 13.8 billion years, there's not been enough time for light to travel from that hot spot to the cold spot to even out those temperatures. So that's a horizon problem. And you say, well, what if they made the universe older and give you more time? It doesn't work, because then it allows you to see even further into space, you see. No matter how long it takes the light to get from there to here, it's going to take it longer to get from there to there, right? It's going to take longer to go the full distance than halfway. So that's the horizon problem. And then we have the monopole problem. Physics allows for the existence of magnetic monopoles, particles that have a single polarity. Like a magnet has a north and a south. Theoretically, you could have a particle that has only a north magnetic pole, or only a south magnetic pole. They're supposed to be produced at the extremely high temperatures of the Big Bang, but we haven't found any. We haven't found any. And that suggests to me that there was no Big Bang. Because if these things are supposed to be produced in the high temperatures associated with the Big Bang, and we don't find any, that suggests those high temperatures never existed. And therefore there wasn't a Big Bang. Now those three problems, flatness, horizon, and monopole, my secular colleagues attempt to solve those three problems simultaneously with inflation. So if you've heard of inflationary Big Bang scenarios, that's an attempt to solve those problems. Inflation is an additional set of assumptions in which the universe begins to expand at a much accelerated rate at a certain point in time. So the universe starts expanding at what we'll call the slow rate, which is actually very fast, but it's slow compared to what comes next. And then it jumps into this inflation phase where it really balloons out. And then it somehow switches off and goes back to the slow rate again, which again is very fast. So, and during that, well, I'm not going to go into the details of how it can alleviate this problem, but I'll just say that it can. It can reduce this problem, maybe even eliminate it. But really, the inflation it's really just another story without supporting evidence. And it has problems of its own, such as how do you turn it off everywhere at the same time? It's called the graceful exit problem. And these are problems that you can read about in standard technical literature. But there are more scientific problems with the Standard Cosmological Model that would not be resolved even if inflation were true. The problem of, for example, the singularity. There's actually really three problems. There's the existence of the singularity. I'm not denying that singularities are possible, but usually in physics, when you're solving a physics problem and you get an answer that's infinity, usually it's an indication you messed up somewhere, right? And so that suggests that maybe we ought to go back. I'm not saying it's impossible, but that suggests maybe you've have a problem there. Some versions of it don't even end up in a singularity, which is interesting. The breakdown of thin physics. We have physics that can explain what happens in extreme gravitational fields, and that's general relativity. And we have physics that can explain what happens when you have a very small space, like subatomic scales, and that's called quantum mechanics. But currently, there is no branch of physics that can explain what happens when you have both of those situations. Intense gravity in a very tiny space, which is exactly the conditions that the Big Bang requires. And so my point is, my secular colleagues have to take it on blind faith that if such a physics is ever discovered, it will even allow for a Big Bang. Isn't that interesting? Finally, the cause of the universe. You realize the Big Bang doesn't actually explain how the singularity got there or why it suddenly started expanding. It's just a story about what supposedly happened afterwards. I think it's ironic. The one thing the Big Bang does not explain is the origin of the universe. Isn't that funny? Because that's what people think it was designed to explain. It's a very unnumbered problem. I think that this may be my favorite because it's easy to understand. It's the question of where's the antimatter? Because remember early on we said that all the matter today, according to the Big Bang, was once energy. And we know that you can take energy and the kinetic energy of particles and turn that into new particles, you can make matter from energy, but every time we do it in the laboratory, we get an equal amount of antimatter. Now, antimatter is the same as ordinary matter, but the charges of the particles are reversed, right? So you've got, in normal matter, you got a positively charged proton. An antimatter particle would have a negatively charged, called an antiproton. And if it was like an antihydrogen, it would have a positron circling it, okay? And so if we make hydrogen, we get an equal amount of antihydrogen, and so on. Every particle we make, you get an antiparticle. Every time we've done it in a laboratory, you get an equal amount. And that seems to be a conserved property. A baryon is just an ordinary particle like a proton or neutron. These are both baryons, right? And so they're a very ordinary particle. There's a Star Trek The Next Generation episode where they do a baryon sweep, but everyone's worried about these baryons. I'm like, that's what you're made of. So it's not really a problem. You're made of baryons. But in any case, you ought to have antibaryons. If the entire universe came, if all the matter in the universe came from energy, you'd have an equal amount of antimatter. And we don't. Our universe is essentially matter only. There's only trace amounts of antimatter, and they're always produced locally by high energy reactions and then almost immediately destroyed, because whenever antimatter comes in contact with ordinary matter, they destroy each other and release energy, electromagnetic energy, and so on. So it's very good that God made the universe matter only. That's a design feature. We don't want equal amounts of antimatter. Thank you, Lord, for doing it this way so that we can be here having this conversation. Distant mature galaxies. The existence of fully formed galaxies was really a surprise from the Big Bang perspective, because in the Big Bang view, I remember when the Hubble Deep Field came out, and eventually the Hubble Ultra Deep Field and so on, and I remember the secular astronomers going, that we were not expecting that. Because you see, in their view, you're looking out, you're looking back in time. It's not really true, but for the sake of argument, let's assume that. And so you say, you ought to be looking back toward the Big Bang, you ought to see galaxies just starting to form. That's not what we see. We see fully designed galaxies, some of them spiral galaxies, that look a lot like the galaxies nearby, as if they were just spoken into existence. And of course, they were. There's the problem of population 3 stars. Stars that we observe in the universe are population 1 or population 2. That refers to the amount of heavy elements that they have in them. In astronomy, any element heavier than helium is referred to as a metal. So we use a different definition than the chemists for metals. But so all stars have metals in them. Their stars are mostly hydrogen and helium gas. Okay, those are the 2 elements that are supposed to be produced in abundance in the Big Bang. And then, but all stars have the heavier elements. They have a little bit of oxygen and a little bit of carbon. And the population 2 stars might have 1,000 times more than that. It's still trace amounts. But here's the problem. The Big Bang, remember, is only supposed to produce what? Hydrogen, helium, a little bit of lithium. Therefore, what would the first stars have to be made of? Hydrogen, helium, a little bit of lithium, right? They can't have the heavier stuff because it takes stars to make that heavier stuff. And therefore, the oldest stars in the universe, some of which would still be around today. I mean, we find red dwarf stars that could theoretically last the age of even the 13.8 billion years, supposedly. And yet, all of these stars that we've measured do have some metals in them. They might have very few, but they have some. And that's a problem in the secular view. So there's scientific evidence that challenges the Standard Cosmological Model that has not been resolved in my mind. There are observations that are consistent with a young universe. And this would seem to be a problem because the Standard Cosmological Model requires millions of years. How do we argue, though, for a young universe? Because the fact is, when you do science, observational science, testable, repeatable science in a laboratory, you really can't measure age, right? I mean, age is not a substance that you can measure. It's not like you can take a rock and scan it with your tricorder and it just gives you the age, measures the agicals or something and tells you the age. It doesn't work that way. The fact is, scientists make certain assumptions about how things change over time. They make certain assumptions about what things were like to begin with, and then they observe the way things are now, and they draw a conclusion about how old something is. And so my point is that, depending on our understanding of history, we're going to draw very different conclusions about the very same evidence. If we accept the secular timescale, the secular way of thinking about things, then there are certain presuppositions that go along with that. Certain assumptions about the past. Secularists tend to believe in uniformitarianism, the idea that rates and conditions have basically more or less been the same throughout history, especially Earth history, but it would apply to the universe as well. And so the way something was in the past, we assume, is sort of like it is today in terms of rates and conditions. Whereas in the biblical timescale, we would say, well, we know there have been at least one or more catastrophes, at least in Earth's past. There's the fall, which affected all creation. We don't know exactly how that affected the universe. We know on Earth it brought about thorns and thistles and things like that. And then, of course, on the Earth we have the catastrophe of Noah's flood, which is responsible for much of the geology that we see on Earth today. So very different. And of course it happens very, very fast. And then the secularists would tend to assume naturalism, that nature's all there is, that everything is explainable in terms of natural law. Whereas I'm a supernaturalist in that I believe that God can do what he wants. I do believe in natural laws because I believe God upholds the universe in a consistent way most of the time. But I also believe God is not bound by natural law. He doesn't have to do it that way. And on some occasions, he seems to suspend natural law for his own purposes. It was interesting. I was reading up a secular criticism of the ICC. One of the guys said that they believe that the origin of the universe doesn't have to be explained by the current properties of the universe. And he said that as if that was just a refutation. Well, that's just silly. And I'm thinking, why? Well, that's a philosophical assumption on his part. There's no reason why the origin of the universe would have to be explainable in terms of present processes in the universe. The origin of a car is not explainable by the operations within the car, is it? Right? And so there's no reason why the universe would have to be that way. But that's a presupposition. And then based on those presuppositions, you draw different conclusions. You look at your rock, you assume uniformitarianism and naturalism, you say, yeah, billions of years. You might look at the same rock, you assume worldwide flood, you assume a supernatural creation to begin with, you say, well, yeah, creation in 6 days, a few thousand years ago. So the problem is not with the evidence. We look at the same evidence and we draw very different conclusions about what it means because of our different presuppositions. And so the secularists very consistently they'll assume uniformitarianism, assume naturalism, and they'll say, how could you not believe in billions of years? And then we look at them and we say, but we know there was a worldwide flood, we know God supernaturally made the universe. How could you not believe in creation in 6 days? How do we get anywhere? Scientifically, the only rational way to resolve a worldview debate, and this is a worldview debate, it's about a debate about different presuppositions. The only way to resolve that is with an internal critique. An internal critique is where you hypothetically assume the starting presuppositions of your opponent and show that they lead to a contradiction. Okay? And it's very powerful. Because what you're going to do is you're going to say, although I don't believe in uniformitarianism, I'm going to temporarily assume it and show that it leads to an inconsistency. So Mr. Evolutionist, I'm going to temporarily assume uniformitarianism. I'm going to temporarily assume naturalism and show that in many cases you actually get an age that is inconsistent with billions of years. And you can't say I've made faulty assumptions because I've assumed your assumptions. And so why it's so powerful. And in fact, most of the arguments that you've seen, scientific arguments for a young Earth or a young universe, are along these lines. And so I'm suggesting that we've been doing a pretty good job of arguing this way. However, most people don't understand that. And so we need to do a better job of articulating what we're doing. I've had a lot of people say that the recession of the moon argument, you assume uniformitarianism. Yes, that's the point. I assumed your assumption and it still gave an age that is wrong by your view. Okay, that's the way we need to argue that. Now, if the old earthers were consistent, if they were rational, and they wanted to argue against us, what should they do? They should assume this. They should assume catastrophism. They should assume supernaturalism and show that it leads to a result that's inconsistent with creation in 6 days. Is that what they do? No. They assume this and show many instances where it gives an answer they like, which is not rational. I will concede that in many cases, if you make this wrong assumption and you make that wrong assumption, you're going to get the wrong answer. I will concede that. But I don't agree with those assumptions. I think it's interesting that my older colleagues, they're really not being very logical when it comes to argumentation. They don't seem to understand that they haven't really proved what they think they've proved. So what I'm going to do is, for the sake of argument, assume these, and we'll find that, for example, the recession of the moon is a good argument for at least a young Earth moon system, right? Because the moon is moving away due to tidal forces. It moves away about 1.5 inches a year. And we'd expect that on the basis of physics, because the moon induces tides on the Earth. The tides get ahead of the moon because the Earth rotates faster than the moon orbits. They pull ahead on the moon and moves it out. And if you run the equation backwards, and you have to do it right, because if you think about it, when the moon's closer to the Earth, the tides would be bigger, wouldn't it? Because the gravity would be stronger. And so it would go even faster, and they get bigger and go even faster, and so on. You have to use calculus to do it right. The relationship is 1 over r to the 6th power. That's the rate at which the moon moves out. And so when you integrate that, assuming the tidal breaking constant has always been constant, that's the uniformitarian assumption. Not that the rate's constant, but that the rate of the rate is constant, if you will. And then when you run it back, you find that the Earth and Moon would have been in a collision less than 1.5 billion years ago. And again, I'm not suggesting this is the true age of the Earth-Moon system. It's an upper limit, because you can't have less distance than no distance, right? That's the absolute upper limit. And this is a problem because, of course, in the secular view, the Earth and Moon system are supposed to be 4.5 billion years old. And yet, the physics, even given their assumptions, the physics shows they can't be more than 1.5 billion years old, which is less than 4.5 billion years old. It's easy enough even the Common Core folks understand that one. So that's a good one to use. Spiral galaxy wrapping. Spiral galaxies actually rotate faster on the insides than on the outsides in terms of their angular velocity. So a star on the inside of this galaxy will make a loop in less time than a star on the outside of the galaxy. Okay? And we've actually measured that in the Whirlpool Galaxy. That's an actual data plot of the velocities of the stars, because the Whirlpool Galaxy, it looks like it's face on, but it's actually tilted a little bit. And so from the Doppler shifts of those stars, we can measure that. And we know how fast they're moving. We know that. And so I thought, how long would it take for this thing to twist itself up beyond recognition? And the answer is it doesn't take very long. So I took those velocities, which have been measured, put them in a computer simulation. There's what happens. This is based on the actual velocities of the stars in the Whirlpool Galaxy. We're at about 100 million years now. Now, in the secular view, galaxies are supposed to be 10 billion years old. I only ran the simulation out to 1 billion years because there was no point in going beyond that. You see what happens? The galaxy very quickly, by the time you're even a few hundred million years into it, the galaxy is twisted beyond what we see in any galaxy anywhere in the universe. There are no galaxies that look like that I'm aware of. I've seen a lot of galaxies, none of them look like that. They're not twisted that much. They're twisted a little bit. I think that God created the galaxies with spiral arms already. There's a lot of spirals in nature. There's even spiral in mathematics. If you've seen my presentations of the Mandelbrot sets built into math, they're already spiral. So God created the galaxies with spiral. They've spiraled a little bit since creation. Now, my secular colleagues are aware of this, by the way. There's no disputing that these arms would wrap themselves up beyond recognition in far less than 10 billion years. There's no disputing that. And so the latest idea is, well, maybe density waves create new ones. And so as the old spiral arms disintegrate, new ones are created by pressure waves that come through and trigger star formation. And that's pretty clever. But there's some problems with that. For one, it assumes star formation, of which I'm very skeptical. Again, we've never seen that. So they're relying on something that's not been demonstrated scientifically. But there's another problem as well. You see, if the actual arms had twisted up, that means the material would be wound up, and then the pressure waves would make the new material. But then the magnetic fields would cancel out, because you see the magnetic fields happen to trace the spiral arms. Now, the thing you need to know is that magnetic fields have to move with the plasma. Plasma cannot move across a magnetic field line. And so, if it was density waves, you would not see that. That shows that it's the actual material that's being dragged along in that direction. So I think that's very compelling evidence against density waves. And there are problems with what would start them anyway. So the bottom line is, if the universe is 6,000 years old, you'd expect galaxies would look like that. If it was even 1 billion years old, you'd expect the galaxies would look like that. What do galaxies look like? Like that. Consistent with creation, isn't it? We have the internal heat of the giant planets. Jupiter actually gives off twice as much energy as it receives from the sun. Thermal energy is taking in 1 unit, giving away 2, and so on, which means it's constantly losing thermal energy. The problem's even worse with Neptune. Neptune gives off about 2.6 times as much energy as it receives from the sun, which means it's constantly losing energy to space. And if it's 6,000 years old, it just hasn't run out of energy yet, because it's pretty big. I mean, Neptune's 4 times the size of the Earth. And so in 6,000 years, it's lost some energy, but it's still pretty warm. It's 72 kelvins, which for its distance from the sun is quite warm. If it were billions of years old, it should have lost all of that. Internal energy should be gone, and the equilibrium temperature should be 58 kelvins at that distance. What do we find? We find it's 72 kelvins. It's consistent with 6,000 years. Isn't that interesting? Magnetic fields are very consistent with a young solar system. And so we find, for example, that the Earth's magnetic field has been decaying. We'd expect that. Magnetic fields are caused by electrical current, right? You can take, maybe when you were a kid, you took a little coil of wire like that and stuck it to a battery. You can make a little electromagnet that way. And electricity encounters resistance, it runs down. And so Earth's magnetic field has been decaying over time. We've been able to measure that for almost 2 centuries. It appears to be an exponential decay. That's what we'd expect, just on first physics principles. The half-life is something like 1,400 years. There's a few other estimates of that. But you run it backwards, you'd find that creation is 20 times stronger. That's okay, that'd be kind of nice. You get increased protection from cosmic rays, that'd be kind of nice. Your compass will work better. Neat. But if you run it back 50,000 years, the Earth's magnetic field would have been 56 billion times stronger than it is today. And you don't want that. In fact, if you go back another 10,000 years to 60,000 years, the Earth's magnetic field would be stronger than that of a neutron star. So, I mean, you don't want that. It's going to rip the atoms in your body apart. That's not what we want. And this is not, we're not in the millions of years here. We're just, just 50,000 years ago. That's nothing in the secular timeline, right? That's a problem. And it's not just a problem for the Earth, it'd be a problem for the other planets as well. Jupiter has an enormous magnetic field, be bigger than the Sun if you could see it. It's very, very powerful. The planets Uranus and Neptune have magnetic fields consistent with their biblical age of thousands of years. In fact, Dr. Russ Humphreys, who is here today, he actually predicted the magnetic fields of these planets based on their biblical age of about 6,000 years. He said the magnetic field of Uranus, for example, ought to be in between the light blue line, you see it, or the dark blue line up there. It ought to be in between those two limits. It's a logarithmic scale. And in the secular view, it really ought to be non-existent. And so when Voyager 2 went through and measured the magnetic field, it was consistent with the prediction. So that's pretty neat. That's pretty neat. Likewise with Neptune. They would not have strong magnetic fields if they were billions of years old. And my secular colleagues say, well, there's some kind of recharging mechanism, the dynamo, that recharges the magnetic fields. All kinds of problems with that model. It's never been demonstrated that that can actually recharge a magnetic field. And it would require, by the way, the rotation axis to be lined up with the magnetic axis, which is not for Uranus and Neptune.